Hey students, welcome. This is a video on section 3.2 of our elementary statistics book. The title of the section is Measures of Variation. Okay, in some of my earlier videos from last week, we learned about measures of center. Remember that a measure of center, such as a mean, median, mode, mid-range, or weighted mean, tells you roughly where the middle of your data set is. What we're going to be learning about today is in 3.2 measures of variation. So instead of focusing on the center or the middle, we're going to be focusing more on, well, how much are the data values spread out? Are they all close together? Are they spread far apart or somewhere in between? And there's some math that we can do to measure variation. So how much variation is there? How much spread of the data values is there? Okay, so variation is the single most important topic in statistics. This is according to our book. So this is the single most important section in the book. This section represents three important measures of variation: range, standard deviation, and variance. So the good news is that the range is easy to calculate. The bad news is that the range isn't that useful. The standard deviation and the variance are both difficult to calculate by hand, but they're also very important and very useful, so we can't skip them. The standard deviation and also the variance are used all the time by statisticians and scientists all around the world as a measurement of, well, we have all these data values, but how much are they spread out? Well, we can measure that, and that's what those two are useful for. Okay, and then, of course, after we learn how to do the math, we'll also be learning about how to interpret and understand the range, standard deviation, and variance. And then, so in this video, we're going to focus on the computation of these as well as their importance in the real world. Okay, so let's go on to the next slide. So when we're using these measures of variation, the three measures of variation we're learning are range, standard deviation, and variance. When we're calculating these, the round-off rule is very similar to the other round-off rules that we've learned before. So you're supposed to carry one more decimal place than is present in the original set of data. Okay? So if, for example, if your data values are have one decimal place, then when you are calculating a measure of variation, you should have two decimal places, which is one more. Okay. All right, so that's good to know. And then we're going to start with the easiest thing to calculate here, the range. Okay, so the range is definitely the simplest measure of variation that there is. And it's just the difference between the maximum data value and the minimum data value. Okay? So difference means subtract. So range equals the max minus the min. Remember that the maximum is the same as the largest data value, and then the minimum is the same as the smallest data value. So we can already see the good thing about the range is that you barely even need a calculator to even find the range. But we can also notice something else here. It's not including many of the data values. It's only including the maximum and the minimum. So it's not going to be resistant. Okay. So before we talk more about the range, let's do an example of calculating the range, and then we'll come back to the properties of the range in just a second. So here's an example from our book on calculating the range. So we're coming back to our favorite set of data values here for Space Mountain wait times. The same data values that we've used in previous sections. And these are taken from our book. Okay, so if we want to calculate the range of these data values, we simply find the maximum, so we just look for the largest number here, and that is 75. Okay, so 75 is the largest, that's the max. And then we need to find the smallest, so we look through all the data values for a data value that's smaller than all the others, which here is going to be 20. Okay, so 20 is the min. And then to calculate the range, you simply use the formula maximum minus minimum. So here that's going to be 75 minus 20, which is 55. And then using this round off rule that I was just talking about, because the original data values have 0 decimal places, we have to have one more decimal place in our answer. So in our answer here, instead of just writing 55, we write 55.0. Okay, so we tacked on one more decimal place than the original data values. So that's, honestly, I want to say it's probably the easiest math in the whole book is calculating the range. You just subtract. But as I was mentioning, we can already kind of see some problems with this, which is that the range is only including the max and the min when we're calculating it. So it doesn't say anything about the spread of, or the variation of all of these other data values. But it sure was easy to calculate. And it still is useful. People do use the range all the time. But, you know, it's not resistant, and it has plenty of problems. It's just very easy to calculate. So what's good about it? What are some important properties? So the range uses only the maximum and the minimum, as we were saying. So it is very sensitive to extreme values. Remember that extreme values are the same as outliers. Okay, so outliers are data values that are unusually high or unusually low. So if they're unusually high or unusually low, that means they're outliers because they're far away from the other data values. The problem with that, obviously, is when you're calculating the range, the maximum is if you have an unusually high data value, that's going to be the maximum. So that's going to make the range be a lot larger. And then if you have an unusually low data value, that's going to be the minimum. And so that's going to make the range a lot smaller. So it's not resistant to outliers. Okay, so yeah, it does not take every value into account and therefore does not truly reflect the variation among all the data values. But hey, it's super easy to calculate, and people still use it. It still has its uses. Okay, so the next thing that we're going to learn about is the standard deviation. Now, the standard deviation of a set of sample values denoted by S, here we're talking about the sample standard deviation, S, is a measure of how much data values deviate away from the mean. So if you're not sure about what the word deviate means, it essentially is telling you how far away the distance between the data values and the mean. And the nice thing about the standard deviation is it measures sort of like, roughly speaking, it sort of measures like the average amount of deviation in that it takes into account all of the data values. So it is a more resistant measure of variation, so it's more useful, but it is more difficult to calculate as well. Okay, and just so you know, we're going to be focusing on the sample standard deviation S, but we're also going to be mentioning the population standard deviation sigma. Okay, so if you haven't seen this letter before, for the population standard deviation, this is a Greek letter. This is called sigma. Okay, and sigma is just a Greek letter, and here it represents the standard deviation for the population. But unless we can do a census, we're not actually going to be able to calculate sigma. We're not going to be able to calculate the population standard deviation, which is why I say we're going to focus on calculating the sample standard deviation. Now, even though we're just doing the sample standard deviation, we can still talk about the population standard deviation, even if we can't necessarily calculate it. Okay? Alrighty, so let's go on to the next slide. So now, this is the first time we've seen an intimidating formula in this class, in my elementary statistics class. I know this looks intimidating. Actually, both of these formulas look intimidating, especially if you haven't done a lot of higher level math courses before. But just because the formulas look intimidating doesn't mean that they're necessarily difficult to use. They can seem difficult, but if you break them down into smaller steps, you're going to find that if you follow my steps when you're doing your homework and your quiz and your exam, they're actually not too bad. Now, the top formula here is the sample standard deviation formula. Now, this is the official formula for the sample standard deviation, and this one is S equals the square root of the sum of parentheses x minus x bar parentheses squared all over n minus 1. So the thing about this is you have to calculate x bar, which is the mean, in order to use this formula. Some people prefer this top formula. I actually prefer the bottom formula. So the top formula is called the sample standard deviation formula. The bottom formula down here, even though it looks more complicated, is referred to as the shortcut formula in our book. Okay? So the reason it's called the shortcut formula is it's used by calculators and software. And I also recommend using this bottom formula. So in this video, I will briefly go over how to use the top formula, and it's on the slides. But the one I really want to focus on is the bottom one, because students usually find the shortcut formula to, even though it looks more complicated, usually it works out better, and it takes less time to calculate. But if you prefer to use the top formula, like if you've taken statistics before, or you just prefer the top formula, you're welcome to use that on your homework, quizzes, and exam. There's nothing wrong with it. I just feel like this one is longer. Usually takes longer to calculate than the shortcut formula. So, and then the other problem with the top formula here is that it's more prone to rounding error. So people usually calculate the top formula using a table. And not only does it take longer, but if you round each of the values, it can actually throw off your answer. So I prefer this one. But let's take a look at the top one first in a calculation. And then after we've calculated the standard deviation, we'll talk more about its usefulness in the real world. But for now, just take my word for it. The standard deviation is very useful. Even though it's a bit challenging to calculate, it's much more useful than the range in the real world. Okay, so coming back to the same data values for the Space Mountain wait times, here's an example on computing the sample standard deviation. So remember that the sample standard deviation is the same as S. So this one right here, with all the steps that are written on the slides, this is going to be how to use the long formula. Okay, so this solution is the long formula. I call it the long formula. The book calls it just the sample standard deviation formula. So in order to do this, in order to use that formula, first you have to calculate the mean, x bar, okay, which is the sum of all the data values divided by n. So this, for the long formula, first you have to calculate the mean. That's not too bad though. You add up all the data values, 50 plus 25 plus 75. Just add them up. You don't have to put them in order. And then you divide by the number of data values. So we've already gone over calculating the mean in last week's videos. So, well, and by last week, I mean, the last time we actually had instruction. Okay. So x bar is the sum of all the data values divided by the number of data values. So when you add them all up, in the numerator you get 430, and then their total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 data values, so you divide by 11. And then of course, because our original data values were to 0 decimal places, that means we round the mean to 1 decimal place. However, we already have a problem here, which is that we're already rounding. So if you want to get a more accurate answer, you might want to write a few more digits. If you're using the long formula, you would want to write a few more digits than this. And try to avoid rounding until you get to the very last step. Okay, so the mean is 39.1. X bar is 39.1. So our goal is to use this formula here, the long formula. It takes a lot of steps. So as you can see in the formula, x bar is right there. So the next step after you calculated the mean x bar is to do x minus x bar for each data value. Okay, so step 2 is subtract the mean from each data value. So that's x minus x bar. So we said that the mean was 39.1. X minus x bar, for each of these numbers, we're going to be subtracting. So like, how did they get 10.9? Well, they just took the first data value here, which was 50. Okay, so x is the same as the data value 50, and then minus x bar is going to be minus 39.1. So in order to get 10.9 for the first one, they just did 50 minus 39.1. Okay, 50 minus 39.1. And so that gives you 10.9. But again, a problem here is that we rounded the mean. So that means these numbers here are also sort of rounded in a way. They aren't actually rounding them, but if you want a more accurate value, you might want to actually write a longer version of the mean with more digits. Okay, but the first one is 50 minus 39.1. The next one How did they get negative 14.1? Well, they're just subtracting. So the next one would be 25 minus 39.1. So 25 minus 39.1 gives you negative 14.1, and so forth. And then you have to calculate all of these for every single data value. And then you write them in a list as they did here. So this is just a list of subtractions, subtracting the mean from each data value. Now the name for the standard deviation comes from the fact that we're doing this subtraction in the long formula. So this x minus x bar is called the deviation. Okay? So 10.9 would be the deviation of the first data value. Negative 14.1 is the deviation of the second data value, and so forth. So this is just a list of all the deviations. And again, deviation basically just means how far are you from something? Like what's the distance between this data value and the mean? And the way you get that distance is just by subtracting the mean from that data value. And the nice thing about this is what it's really doing when we're calculating all these is we're taking into account the spread of each data value from the mean. But this is still the long formula, so I don't recommend actually doing this when you're doing your homework because this takes a long time. Okay, so step 3 is to square each deviation. So that's not too incredibly difficult because we've already done step 2. We've already subtracted the mean from each data value. So these are all of the deviations, and then we square each one. However, you should do this on a calculator for sure. So like, I'll just show you what you would type in to get this first one. So for this first squared deviation, you would definitely want to do this on a calculator. And depending on your calculator, you might type it in a different way. But here you just take the first deviation, which is 10.9, and you square it. Okay, so 10.9 squared equals 118.81. Okay? And then you just continue the process for all of these data values. So for example, to get the square of the fourth deviation, you would do negative 4.1 squared. And the thing about it is when you square a negative number, it actually becomes positive. That's why all of these squares are positive numbers, even though some of the deviations were negative. Okay? So, the only nice thing about the long formula is it helps us kind of understand what the standard deviation is measuring a little better. But we're only about halfway through calculating using the long formula. So it's not usually recommended, at least I don't recommend using the long formula. But it's up to you. If you prefer to use the long formula, knock yourself out. One thing that you should take note of, though, is here they're not rounding. So ideally, you want to round at the end. And this is true just in math in general, or any application of math to science. You don't really want to round anything until the very end of the problem. So technically, when they rounded the mean back here, that probably wasn't the best idea. Like instead of writing 39.1, you know, if it has more digits, I'm not sure if this one in particular had more digits, but if it had more digits, you should probably just go ahead and write them and not round until the end. But that's just generally a good strategy So I'm just going to write that up here. So don't round. Okay, don't round until the end. And by the end, I just mean the very last step. And that's just true in general in math and science, physics, chemistry, anything really. Because if you round during the middle of the problem, you can create what's called a rounding error, which would mean that your answer at the end might not be correct. Okay? If you're rounding in each step, it can throw off your numbers and give you an incorrect answer at the end. This is what they did in the book. They rounded the mean, but I don't recommend that. Okay, I recommend you don't round until the end. Okay, step 4, sum all the deviations. So remember that sum means add. Okay, so for the long formula, because we've calculated the square of each deviation, when they say sum all of the deviations, they actually they aren't being that clear. They mean sum the square of all the deviations. So you square each deviation, which we did in step 3. So really they mean sum the deviations squared. Okay. In other words, you just add up all the numbers that you got in step 3. Okay, so we're going to add up all of these numbers here, so 118.81 plus 198.81 and so forth. Add up all these numbers on a calculator. Simply press the plus button until you're done typing them all in, and then press enter. Okay, so when you do that, you should get 2,740.91. Again, I don't recommend rounding. Even if they haven't rounded here, whether they have or haven't, it's not a good idea to round until the very last step. Okay, so step 5 is to divide the sum by n minus 1. Now remember that n is the same as the number of data values. So n minus 1 is just going to be the number of data values minus 1. So here we had 11 data values. So that means n minus 1 is going to be 10. 11 minus 1 is 10. So in step 5, all we do is we take this number here, the 2,740.91 that we got from step 4, and we divide by 10, which is n minus 1. And then on a calculator, or if you know how to do decimal division in your head, it's basically just going to move the decimal. Because we have 1 with 1 0 after it, it's going to move the decimal 1 place to the left. Okay, so that's just going to move that 1 place to the left. But you won't always have 10 as your denominator, so you want to do it on a calculator. Okay. This one's easy to do, but your n minus 1 could be like 37, which would be very tedious and time-consuming to do by hand. Okay, step 6, take the square root of that quotient. Now, quotient means division. So they're talking about this formula here. You take the square root of it. So what we got on step 5 was 274.091. And in step 6, we want to take the square root of that number. So square root of 274.091. Remember that square roots kind of look like a check mark, and there's something that you definitely want to do on a calculator. So you're just going to look for the button on your calculator that looks like a check mark. You would type in, you would probably press the check mark button first, the square root button, and then you would type in the number, and then you'd press enter. Okay, and then step 6 is actually the last step. Okay, so at this point, we're at the end of the problem. So we're going to go ahead and round. So when you plug it into your calculator, you should get about 16.556. But then we want to go ahead and round now. And so using our round off rule that we talked about at the beginning of this lecture, we want to carry one more decimal place than is present in the original set of data. So in this problem, the original data values had 0 decimal places. So we want to have one more than 0, which is 1 decimal place. Okay, so that's why they rounded this to 1 decimal place. And if you need a quick refresher on rounding, when you're rounding this, we're looking at 1 decimal place, so we're looking at this 5 here. And then because the next digit is 5 or higher, they rounded up. So if the next digit is 5 or higher, you round up. If the next digit is 4 or lower, you round down. Now rounding down just means you keep the number the way it is. Rounding up means you increase that digit by 1. So here they rounded up. Here they rounded up because the next digit was 5 or higher. So 5 plus 1 is 6. That's how we got 16.6. So that is the long formula. I call it the long formula because it takes a long time. Even though we only had 10 data values, it takes a long time and a lot of calculation to get it done. And like I said, the other problem that you might run into if you use this long formula is just rounding. So if you're doing your homework, you probably don't want to round x bar, which is your mean. So you might get x bar, a sample mean that's got a lot of digits, which can take a long time to type into your calculator. Okay, and then what that means is that when you're subtracting from each data value, that means all these numbers can have a lot of digits, which just takes a long time to write down. And then when you square each of those numbers, you're going to have even more digits. So you're going to have even more numbers. It's just very time consuming, all these steps. And then you add up all the numbers. That's not so bad. Well, you add up all the deviations squared. So you square each deviation, you add them up. So step 4 isn't too hard. Step 5 isn't too bad. You just divide by n minus 1. Step 6 isn't that bad. So the square root of the number isn't too bad. So really the last 3 steps aren't too hard, but I want to say step 1, step 2, and step 3 are very time consuming, and you probably shouldn't be rounding, which means you're going to want to write a lot of digits, and it'll just take a long time, especially if you have more than 11 data values. If you have like 20 or 25 data values, this could take forever. Okay? So that was the long formula. If you prefer to use it, you're welcome to, but it should help you at least get an understanding of what the standard deviation is. So the standard deviation is really, it's when you square each deviation, or you square the distance between each data value and the mean, and then you add them all up and divide by n minus 1. It's almost like you're taking sort of like the average of all of those deviations. It's very, very close to that. The only difference would be that you're actually squaring. So it's really the average of the squares of all the deviations. But the nice thing about it is because it takes into account all of the data values, if you have a very high data value or a very low data value that's an outlier, it's not going to affect the standard deviation nearly as much as it would something like the range. Okay, so let's take a little break from the computation. I want to do the shortcut formula after this, but let's go ahead and go back to why the standard deviation is so important and so useful. So let's talk about that. So going back to these slides, important properties of the standard deviation. Okay, so the standard deviation is a measure of how much data values deviate away from the mean. As we could see from the long formula that we just sort of went over in some detail, because we're subtracting each data value from the mean, and then we're squaring, and then we're dividing by the number of data values minus 1, it's sort of like, it's pretty similar to the idea of finding the average or the mean deviation or the mean variation between each data value and the average, which is the mean. Okay, the value of the standard deviation S is never negative. That's important to know. And the reason it's never negative is because of, if you go back to the long formula that we just went over, in step 3, because you're squaring all of these numbers that you got from step 2, all of these numbers are positive. So then in step 4, you add up a bunch of positive numbers, which is still positive. Then you divide by n minus 1, which is always positive. And then square roots are always positive. So that's why the standard deviation is always positive. Or it could be 0, in which case, if you have a standard deviation of 0, that would mean that all the data values are exactly the same. And the way you would get 0, well, if they're all exactly the same, then the mean is going to be the same as every individual data value. So x minus x bar, each deviation is going to be 0. So it's all of these numbers would be 0. You square 0, you still get 0. You add up 0 and divide by a non-zero number, take the square root, it's still 0. Okay, larger values of S, the sample standard deviation, indicate greater amounts of variation. Okay. Larger values of S indicate greater amounts of variation. So we just said that if S equals 0, that means all the data values are the same. There's no variation. If S is larger, like if S is 1.3 or 2.5 or 7.8, the larger it is, that means the more on average data values are varying or deviating away from the mean. Okay, next page. Other important properties of the standard deviation. The standard deviation S can increase dramatically with one or more outliers. However, it's not as bad as the range. Okay, so because it does take into account all of the data values, it's definitely, even if it's not resistant, it's definitely more resistant than the range, because the range only has the maximum and the minimum in its formula, whereas the standard deviation includes all the data values. But what they're saying here is if there are outliers, it does dramatically increase the standard deviation. However, it's still a lot more resistant than the range. Next thing, the units of the standard deviation S, such as minutes, feet, pounds. I said feet, that's, dude. Feet, pounds, are the same as the units of the original data values. Okay, so your original data values are going to have the same units as your standard deviation. The last important property, the sample standard deviation S is a biased estimator of a population standard deviation sigma, which means that values of the sample standard deviation S do not center around the value of sigma. Okay? So, roughly speaking, we said that bias is generally a bad thing, and that's true. So we don't really want a biased estimator. We want an unbiased estimator. And later on in this video, we'll be learning how to calculate the variance, which is considered an unbiased estimator of a population variance. Okay? But for now, we're just going to note that the sample standard deviation, so just for the data values in our sample, is a biased estimator. Estimating means sort of guessing about the whole population, and bias is not good. So, roughly speaking, this is not a good thing. It does help you estimate the population standard deviation sigma, but we would actually prefer to use the sample variance to estimate the population variance because that's actually an unbiased estimator, which we'll talk about more later. Okay, so let's go back to calculation. So I wanted to show you how to use the shortcut formula, which I usually recommend for most people. So we went through the long formula. The long formula, some people use a table. They'll make a table to help keep it organized. But like I said, I don't usually recommend using the long formula. So I'm not going to take a bunch of class time just to, make a table for it because I feel like it's just too long. We've gone over it to kind of understand the standard deviation, but when we're actually just trying to calculate the standard deviation, I recommend using the shortcut formula. So how do we do that? Well, it's really much quicker, which is why calculators and computer software use this shortcut formula. Okay, but it's really a matter of what you prefer. You're welcome to use other formulas for the standard deviation than the one that I like to use. So you can use the long formula and you can make a table if you prefer. Okay, so for the shortcut formula, it looks more intimidating, and we do have to understand the different parts of it, but much easier to calculate. So I'm going to go ahead and grab my calculator. So looking at the shortcut formula, which is already written out right here, we can focus on each individual part of it and calculate each part of it in our calculator, then plug in the numbers like they did here, and then quickly calculate the standard deviation. And of course, in the modern world, calculators also have a way of entering in your data values, and they'll automatically calculate the standard deviation. However, I like to show people how to calculate a standard deviation without having the calculator do all of the work for you, just so that we can understand the math and also be able to do the math for the sake of understanding it. Okay, so let's take a look at this formula. So rather than having multiple steps, we kind of have to just focus on individual parts. So here we have n, which is the number of data values. So here n is going to be 11. Okay. Actually, I think I'm going to write up here. Okay, so n equals 11. That's the same as the number of data values. There are 11 data values here. So that's that right there. The other thing we need is n minus 1 down here. So in our denominator, we can see that we have n times n minus 1. We've already talked about n minus 1. It's just here it's going to be 11 minus 1, which is 10. So here n minus 1 equals 10. Okay, those are the easy things to understand. We have a square root, but we're not going to actually plug in the square root into our calculator until the end here. Okay, so now let's focus on the intimidating part of the formula, which is this right here and that right there. So this one right here is called the sum of x squared. Okay, so this right here is the sum of x squared. It's called the sum because it has the sigma notation, which means you add up the squares of all the data values. Okay, so sum of x squared is the way we read that. And it means we square each data value and we add them all up. Okay, so let me switch to just my camera for a second. So here, so I have room. Sum of x squared is what we're focusing on right now. It means we square each data value and add them all up. So here, our data values are 50, 25, 75, and so forth. So we're going to the first one's going to be 50 squared. The next one's going to be plus 25 squared, and so forth. Okay, so we're going to have 50 squared plus 25 squared plus etc. I'm going to put dots because this board isn't that big. Just to show you that we're continuing this process. So we're squaring each data value and we're adding them all up. Okay, so looking at these, 50 squared plus 25 squared plus 75 squared plus 35 squared plus 50 squared plus 25 squared plus 30 squared plus 50 squared plus 45 squared plus 25 squared plus 20 squared. Okay, so without writing them all down, I think we get the pattern. So if we calculate these, if we type them into our calculator, depending on your calculator, hopefully it has a button that says x squared. If not, you'll have to use the exponent button, which very much depends on which kind of calculator you have. But my exponent button actually looks like sort of like an up arrow. So I would do 50 to the second power plus 25 to the second power, and so forth. And then once I've typed all of these in, then I would just press enter. And that's going to give me the number that they got here, which is 19,550. Okay. So this is 19,550. All right, and this is called the sum of x squared. And you'll notice in the formula there are actually parentheses around this. And the square is inside of the parentheses, so it's applying to each data value x. Okay, so let's take a look at the rest of the formula. So we already have n. We have n minus 1. We have sum of x squared, which is up here. And now the next thing we need to calculate is parentheses, sum of x, parentheses squared. So now we're looking at this right here on the top right corner of the formula. Parentheses, sum of x, parentheses squared. Okay, so for that part, we really just need to understand what it's saying. So the sum of x squared, which we just calculated, means we square each data value and then we add up all those squares. This one, parentheses, sum of x, parentheses squared, actually looks very similar to what we just calculated. So what's the difference between what we just calculated, and this? Well, you'll notice, if I get out of the way, that with this first one, the square is applying to each data value. So we're squaring each data value and adding them all up. Whereas for the sum of x quantity squared, or parentheses sum of x parentheses squared, this actually means first we add up all the data values, and then at the end we square the result. Okay, so let's see what that looks like. So because the square is outside of the parentheses, that means we add up the numbers first. Instead of squaring each data value individually, we add up all the numbers first, and then we square the sum. Okay, so that's going to be parentheses 50 plus 25 plus ... Continue the pattern. All the data values all the way plus 20. So here, because of the way order of operations works in math, we have to add up all the numbers first and then square the result. Okay, so we add all these up first on our calculator, and then we square the result. Although on most calculators, you should probably be able to just type this in all at once. So 50 plus 25 plus 75 plus 35 plus 50 plus 25 plus 30 plus 50 plus 45 plus 25 plus 20. So when you add up all the numbers, you should get 430. And this is if you want to calculate parentheses sum of x parentheses squared in 2 steps. But like I said, on most calculators, you should actually be able to calculate this whole thing all at once by just typing it in. But anyway, 430 squared gives us a rather large number. So it gives us 1,84900. So that's going to be 184,900. All right, so that is parentheses sum of x parentheses squared. And once you calculate n minus 1, and then you also calculate parentheses sum of x squared, which was the 19,550, and then the last thing we calculated was parentheses sum of x parentheses squared. That gave us 184,900. Then we're ready to just go ahead and plug everything into the formula, finally, okay? So looking at the formula here, you can see that they've plugged it in already. So I'm going to go ahead and write down the whole thing, though. I want you to see the math written out. So S equals, let's see how they got this. S equals the square root of n, so n was 11, times sum of x squared. That's going to be times the 19,550. Okay. I'm going to go back to my writing in just a second, but it's getting hard to read on the video, so I'm just going to close that for a sec. So we've got 11 times 19,550. That's n times sum of x squared. And then we have here minus parentheses sum of x parentheses squared. So that's going to be minus 430 squared, which we said was 184,900. 900. Okay. And then this is all over n times n minus 1. So that's going to be all over 11 times 10. Okay. So as we can see there, we just plugged in all of those numbers that we calculated into various parts of the shortcut formula. All right, and then once again, you should be able to just type all of this into your calculator all at once if you want to. But if not, you might want to just take a couple of steps to work it out. So let's go ahead and finish this. So if we want to do it in multiple steps now, what we would do is we would simplify this numerator of the fraction. So we would do 11 times 19,550 minus 184,900 on our calculator. And that will give us 30,150 for the numerator. Okay, so we have the square root of 30,150 all over 11 times 10, and 11 times 10 is 110. Probably don't need a calculator for that, just your times tables. Okay, only thing to notice here is the square root goes around this whole fraction. So then if we do 30,150 divided by 110, that gives us a decimal. And then if we take the square root of that decimal, so if we do the square root of the decimal, which is 274.090909, so if I type that in, I'm going to get 16.555, and it goes on forever. Maybe not forever, but it goes on for a while. But we don't need that many digits. So this is 16.555 or 556. Okay, but then once again, we've waited until the very last step to round. So now notice I hadn't, because we don't have any decimals here, it wasn't really an issue. But if you did have decimals when you're using the shortcut formula, once again, you wouldn't have wanted to round any of those numbers. You would only want to round on the very last step here. And then using the round off rule that we already talked about, we want to have one more decimal place than what we started with. So we started with data values that only had 0 decimal places. So now if we have one more decimal place than 0, that gives us 1 decimal place. But we already dealt with this on the long formula, so it's a little repetitive here. So this rounds to 16.6. Okay, so same exact value for S. S is the sample standard deviation. Okay. Now the shortcut formula took quite a while to explain, but I still feel like it's faster in most cases than the long formula, what I call the long formula. But the disadvantage of the shortcut formula is that it doesn't actually show you what's going on. It's just usually easier to calculate with, if that makes sense. Okay, so let's go back to the slides. And you know what I'm thinking? This video is already starting. It's already close to an hour, so I'm probably going to make this be a part 1 of this section, and then we'll do part 2 of this section in a separate video because I'm getting pretty tired here, talking for an hour now. Okay, so let's go back to the slides. The only thing to note here in the slides that I didn't write down when I was working out the problem is that it says 16.6 minutes. So with the 16.6 minutes, the reason it's minutes is because if you look at the original data values, they were measured in minutes. So they were wait times on a Space Mountain ride at Disneyland, or sorry, Disney World. And then, because those were measured in minutes, that means our standard deviation is measured in minutes. And this standard deviation of 16.6 minutes is just measuring sort of the average variation of the data values from the mean. Okay, so how much are they spread out from the mean? All right, so up to you whether you want to use the long formula, which have all these steps on the slides, or the shortcut formula, which I just wrote down in great detail. But for most people, I would recommend the shortcut formula because it's quicker and it's less likely to have rounding error in most cases. I wouldn't recommend using both unless you want to be like a extra thorough or something and you want to learn every single way to do a problem, but you might get them confused, so I would just pick one or the other. Either the long formula with all the steps or the shortcut formula, and then recommend doing it the way I do. Okay, so like I said, considering how long this took to explain, this video is already over an hour, so I think we're going to have this be part 1. So what we just did 3.2 measures of variation, and this is going to be part 1. So this is going to be the first video covering section 3.2 because it is a big section. Now in part 2, I'm going to cover the rest of the slides, the PowerPoint slides, for section 3.2. So we're going to be learning about the range rule of thumb, and then we'll also be learning about the empirical rule. Okay? But for now, we've learned about the range, the standard deviation, and then in part 2, we're also going to talk about the variance. So if you go back to this slide here, you'll note that we've talked about the range and the standard deviation, but we still need to talk about the variance. So we'll talk about that as well in part 2 of this video. Okay? Thanks for watching. See you on the next video.